To explain advanced propulsion systems for colonizing Mars. Thank you.
Thank you. All right. I'm Joseph Parker. I've got an MD and MSc. I tell my children it stands for Mad Doctor, Mad Scientist. They believe me. This will be interesting. So we're going to look at the different propulsion systems that might be used to get us to Mars. We're going to be looking at things that are available now, not fusion drives or warp drives as much as we would like to see them. So you've got to get your giant spaceship into orbit. Luckily, we have companies who are working on that and are doing a very good job. SpaceX has the Falcon Heavy, which everyone likes, because they should be launching one in a few days. If it gets into space safely, then we can get 63,800 kilograms into orbit, low Earth orbit. Where's the sensor on this thing? Where's it reading from? Well. Okay, problem 2, get yourself to Mars. After you've got your giant spaceship into orbit, how you do that will determine how much usable mass you have in Mars orbit. So your method of propulsion is very important. Specific impulse is a measure of the number of seconds that one mass unit of fuel, 1 kilogram, will produce an equivalent amount of thrust. There's different ways to consider specific impulse. It can be by mass or by weight. If you do it by mass, then you have to multiply by the gravity of Earth, 9.8 meters per second squared, or 32 feet per second squared. So you have 1 kilogram of fuel, and with the space shuttle main engines, you're looking at about 450 is the best they can do in orbit, not down here. Down here, the atmospheric pressure inhibits the rocket a little bit. Specific impulse is not as good when you're taking off as it is later in orbit. So space shuttle main engines burning hydrogen gives you about 450 seconds of thrust, which means that for 1 kilogram of fuel, you can produce 1 kilogram times 9.8 meters per second squared, so 1 Newton of thrust for 455 seconds. That is not much different than what we've been doing all along. If we look at where our rockets are now and where they were back in the 60s, the engineers here who were around in the 1960s and 70s completely understand everything that's being used by SpaceX now. Nothing has been invented that's new. The main thing SpaceX has been able to do is make it much more affordable and make it reusable. And reusable wasn't thought to be practical. To land something 14 stories tall back down did not seem practical. So mass plus kinetic energy equals momentum. To increase the thrust, you have to increase the amount of mass moved or the speed that it leaves the rocket engine. Okay? Velocity gives you your kinetic energy. Kinetic energy of atomic particles is equivalent to heat. Kinetic energy is transferred to particles by heating or accelerating them. In rockets, we burn a fuel with an oxidizer. It produces its own heat, and the propellant are the resultant byproducts of the chemical reaction. Kinetic energy is transferred to particles by heating or accelerating them. In most modern rocket engines, that's supplied by combustion. The chemical agents react, producing heat, and the resulting compound is the propellant. So high thrust engines get us to orbit, and this is a modern chemical rocket engine. So you've got 2 turbo pumps, 1 pumping fuel, 1 pumping oxidizer into your combustion chamber. You're burning it at a certain heat. Now there is a limit to the amount of chamber pressure this device can withstand. There's a limit to the amount of heat this device can withstand. You can cool the nozzle, and that's cool with regenerative cooling. You can somewhat cool your combustion chamber, but to a degree you're defeating your goal because you're cooling down your combustion chamber. But you still don't want it to melt. And these have become incredibly efficient at getting the most energy they can out of their chemical rockets. So So in 1964, Saturn V F1 engine had a thrust of 6,700 to 7,700 kilonewtons, specific impulse of 263 at sea level, 304 once they're in orbit. And after a little more than 40 years of research, the Merlin thrust is 845 to 914 kilonewtons with a specific impulse of 282 to 311. Why is there very little improvement? They're both using the same fuel, RP-1. Once again, the genius of SpaceX is not that they've invented some new type of rocket, it's that they've made them affordable and reusable. So our rocket engines now are more economical, but not better than what the engineers were able to do in the 60s and 50s. Why not? We have iPhones, we have all this Star Trek stuff that we watched in the 60s and didn't think we'd have till the 22nd century. Limitations of current engines. Power source is chemical. RP-1 liquid oxygen. This burns at a specific heat. You can use liquid hydrogen, but then your volume is about 7 times greater than if you use RP-1 because it's not very dense. Then you end up with huge tanks like the big orange thing that we had on the space shuttle. You've got to move that through the air, by the way. Big tank, lots of air resistance if it has a large surface area, or the area that's going through the air. It's limited by the combustion temperature. This has a finite combustion temperature. It's not going to burn any hotter. The chamber pressure, the heat tolerance of your materials, the pump speed. Modern turbo pumps are incredibly efficient and insanely powerful. The Space Shuttle main engines, their fuel pumps could empty an Olympic-sized swimming pool in a matter of seconds. Are there more efficient options without sacrificing thrust? NERVA. NERVA was a nuclear rocket engine. You use a thermonuclear reactor, a uranium-238 and 235. You've got enough 238 there to cause it to heat up. It gets real hot. You throw liquid hydrogen on it. That liquid hydrogen comes flying out the nozzle at high speed because you've got your energy without combustion. You've got your nuclear energy. And it gives you thrust. Now, these were able to get up to about over 900 seconds of thrust in the ones they tested, and they said they could have easily gotten up to 1,000 seconds of not thrust, specific impulse. Apologize. So they're about twice as efficient as regular rocket engines. Well, what's the downside? Well, it uses fissionable material to heat a chamber, flow propellant and all that through the heated chamber. It's simple. It's a nuclear reactor heat exchanger and exhaust nozzle. All you had to do is have some plumbing. Some of the reactors used rods that would rotate. They had, I think it was beryllium on one side and carbon on the other, so if they put the carbon toward the reaction, it slows down. They put the beryllium toward the reaction, it bounces the neutrons back in and heats up. Very, very smart people designing this. It was effective. They tested it, and it worked. Single stage to orbit would be possible with this type of engine. The downside, radioactive, politics, and mass. You don't just have the mass of the engine, you have the shielding required to keep any of that radiation from nailing your astronauts. You start very rapidly absorbing your benefits by adding this huge mass. And the dang hippies who don't like radioactive things. Let's look at ion drives. There are many different forms of ion drives, and a lot of people want to use this. What do ion drives use? Almost always xenon. Why don't they use argon or something more common? Well, if I can throw something 100 miles per hour, and I'm in a boat and I want to go that way, I can throw softballs or I can throw bowling balls. If they're both going to go 100 miles per hour, I'll get a lot more speed out of that bowling ball than I do the softball. So the xenon atom, being more massive than an argon, helium, or neon or other noble gas atom, is going to give you more thrust per particle thrown. They're much more efficient. There are electrostatic and electromagnetic. The electrostatics are like the Hall thrusters. Picture this thruster creating a cloud of electrons outside the thrust chamber, and the ions chasing that cloud of electrons. The plasma is held in a magnetic field instead of a grid. Other ion thrusters use a grid, and those grids can degrade, so they have a limited lifespan. But everything has a plus and minus. If these were perfect, the others wouldn't exist. So the specific impulse is about 1,600 seconds on average. Now, one quick way to think about the specific impulse is to multiply it by 10 in your head, and that's how fast those particles are leaving that rocket. Because 9.8 is pretty close to 10. So these things are leaving at about 16,000 meters per second. The particles are leaving that engine. For the Space Shuttle main engine at 450 seconds impulse, you're looking at about 4,500 meters per second that they're leaving. So you go from 4,500 to 16,000, that sounds great. So for every kilogram of propellant, not fuel, because you're not burning this krypton or xenon, it's a propellant. You have to have another energy source to come in, ionize heat, and eject it. So whereas the chemical engines produce their own combustion temperature, the ion drives do not. That's one of the downsides. So 1,600 seconds average up to 8,000 seconds of thrust. So 1 kilogram of propellant would give you 8,000 seconds of 9.8 Newton thrust. Okay, well that's pretty neat. Producing about 0.6 newtons, up to 60% efficiency, using 10 kilowatts. At the 8,000, you're looking at about 80,000 meters per second. So 0.6 newtons. That's not a whole bunch. So the problem is they can heat this stuff, they can throw it out the back, but they can't heat that much. The mass fuel flow is small. Whereas the Space Shuttle main engine is emptying an Olympic fuel tank, Olympic swimming pool every few seconds, these things are firing off milligrams, and sometimes less than that, micrograms of material at these high speeds. Gridded ion thrusters, they can produce up to 50,000 meters per second at 80% efficiency, a little better, giving a thrust of 0.092 newtons. That's not better. If you're trying to move a 63,800 kilogram craft and you've got things firing with it, you're going to need a whole bunch of them. And then the high-field electric propulsion, which is kind of neat. They use cesium or iridium as a liquid metal sent through a tube. An electric current pulls the ions off at high speed. It's a really neat thing. Not that much more powerful. The Vasmer engine being designed by Dr. Cheng Diaz in Houston. It has been promoted as a good method of propelling us there. It has your xenon tank, and then you put that xenon into your first chamber and you ionize it using radio frequencies. Once it's ionized, you can move it around electromagnetically. So they move it into the second chamber, have superconducting magnets to keep it from touching the sides, and they use another burst of radio frequency to heat it, and then eject it out the back. So it looks like a great design. So variable specific impulse magnetoplasma rocket. Now, one of the downsides, it uses xenon. You won't be refueling it on Mars very easily, or on an asteroid. Uses radio waves to ionize it, confines it in a magnetic field, heats it with more radio waves, vents the heated plasma out the back, can be throttled. Low gear, 3,000 specific impulse, thrust of 400 newtons. Now we're talking, that's pretty good. Mid gear, 15,000 specific impulse, thrust of 80 newtons. High gear, 30,000, thrust of 40 newtons. What's the problem here? When you're looking at low gear with a specific impulse of 3,000, right? That would mean your particles are coming out at about 30,000 meters per second. When you're looking at high gear, where your specific impulse is 30,000, so they're leaving at about 300,000 meters per second. So about 10 times. Does it take 10 times more power to go 10 times as fast? No, it takes 100 times more power. And that's where we run into problems, because whereas the chemical engines produce their own heat and combustion and all that, and all you do is burn the stuff and go, these require enormous amounts of power. Now, they need exotic propellants, doesn't produce its own power, needs an outside power source. Solar is about 50% efficient with latest technology. Nuclear is massive, expensive, Chernobyl flashbacks, but it was flown in 1987. Topaz 1 was a 5 kilowatt reactor. It would last for 5 years, weighed 320 kilograms. That's a pretty good power source. Pretty neat. There were, some very bright people designing these things. If you took a Topaz 1 reactor producing 5 kilowatts of power, and I misspelled use, a current ion drive, it would provide very little thrust for a large Mars landing craft. If you use multiple reactors, 10 reactors gives you 50 kilowatts for 5 years, massing about 1,600 kilograms. So this is all in-space propulsion. You're not going to be lifting off a planet with this thing. As a matter of fact, if you use the Vasmer drive in Earth's atmosphere, it produces a negative pressure. You're going to actually be sucking air into it. So solar electric would require a very large solar array. It could produce about 50 kilowatts of power, and NASA's developing 50 kilowatt ion drives, so pretty powerful drives. And if you put 4 of these on your craft, you could power a Vasimir or other ion drive. I'm not saying Vasimir is the best way to go. The Vasimir weighs 10,000 kilograms for the 200 kilowatt version. You've got 63,800 kilograms. Your propulsion system is going to be 10,000 of that. That's much more massive than some of the other options. So solar, nuclear, electric. So what we come down to is that you could lift a Saturn V off this planet, put it into orbit with 1 proton. You could fire 1 proton off the back of that rocket and put that thing into orbit if you could put enough energy into that proton. Another thing is that the Tsiolkovsky rocket equation is, of course, it's not incorrect, but it's incomplete. Tsiolkovsky was a brilliant guy. In the 1880s, he wrote down all this stuff. He didn't know about Einstein. Einstein wasn't around yet writing his cool stuff. In the early 1900s, Einstein wrote that the faster something goes, its momentum has energy, and that energy has mass. These particles, when you start talking about 300,000 meters per second, what's the speed of light? 2.997 times 10 to the 8th meters per second. You're starting to go appreciable percentage of the speed of light. And you're adding mass to these things with your energy. That is a quick curve that goes this way, where the amount of energy you have to put in to get more thrust out of that goes down dramatically. So we need a way to ionize or propel subatomic particles at a much more efficient way so that they don't have to get up to super high velocities. I mean, the Nerva would have got a single stage to orbit at 1,000. That'd be 10,000 meters per second. Let's say 20,000 meters per second. But you have to be able to ionize and thrust a large amount of mass. Our modern ion drives don't do that, though the Vasimir's size limits its usability. Some of the other ion drives are very small. You could hold the thing up. You could use a number of those, and this is a NASA design for a deep space mission. You could use a number of those on the back. The most practical and immediate way to get from Earth to Mars in the shortest amount of time is still nuclear thermal. There's nothing that beats the thrust for the weight, and your power is generated for years. So you could cycle that thing back and forth. You could thrust halfway there, reverse it, and thrust it back down. Because the United States chose not to launch nuclear objects into space does not mean that other countries will not. Soviet Union obviously did many times. They had nuclear-powered satellites. China or Russia could choose to read our designs on the Nerva, build it, launch it, and have something that would travel much more quickly through space than anything that we have. And they're not limited by what we decide is politically acceptable. So we have to be aware that other nations are going to do this. There will be nuclear reactors in space, I guarantee you, long before there are fusion reactors in space. Any questions? I know I spoke like an auctioneer. I apologize. Last time my 5-minute warning came up, I swear, after like 30 seconds.
How far do you estimate we are from actually having fusion power in space?
The problem with fusion power is either neutronic or aneutronic. If you're using tritium and hydrogen and things like that, you're producing a lot of neutrons. You have to shield your crew from it. If you want aneutronic fusion, then the only practical way is to mine the moon, I know some people don't like that, and get your helium-3, because helium-3 is aneutronic, meaning the fusion produced from it does not put off a lot of neutrons. But let's say you have a little fusion reactor, and you've made it work. You're producing a lot of X-rays, gamma rays, photonic radiation. You don't have, you can cool it. You could run your liquid hydrogen over it and thrust it out the back, but you're still going to have to shield from all that. Until we have a production facility on the moon to get the helium-3 and to build a large enough craft to safely use fusion power, it's not going to be practical. So we need to have a shipyard on the moon. Spaceships will not be built anywhere except on the moon in the future. They won't be built on Mars. They won't be built anywhere else. The moon has everything we need. It has our titanium, it has our aluminum. We have 3D, we could put a 3D printer there, we could smelt using solar power, and we could 3D print a massive ship. So the SpaceX engines, the Merlin engines, can put 63,800 kilograms into low Earth orbit here. 1/6 gravity. How much could they put into low lunar orbit? Well, if we assume 6 times 60,000, 360,000 kilograms. You could build a cruise ship on the moon and just about launch it. Then you're talking about shielding, water. Another way to produce power, which would be very, very effective, would be to have your liquid hydrogen and oxygen tanks burning in an internal combustion engine similar to what the United Launch Alliance uses. You run the steam back through your heat exchanger, collect your water, and pump it into the walls of the ship. So as you are traveling, you are increasing your shielding. So all you put is hydrogen, liquid oxygen into orbit. You burn it through your IC, produce electricity to run your ion drive, and produce the shielding to help protect you on your way there. United Launch Alliance built a small internal combustion engine. They test it. It's about 80% efficient, whereas gasoline engines are about 20% efficient. It could run at 12 kilograms per hour was its maximum output, at 140 megajoules per kilogram for the energy content of hydrogen. You're looking at about 333 kilowatts for 12 kilograms per hour. That's quite a bit of power. And that thing I could hold in my hands up here. It is not a big engine. It's a tiny little 4-cylinder designed in the 1930s. They used a 1930s design because they always overheated. And when you're burning liquid hydrogen, you want something that heats up. Otherwise, you're going to freeze your engine up. Yes, sir.
Have you thought about a liquid metal type reactor like thorium, which can reduce a lot of the safety concerns and allow you to get very effective designs? University of New Mexico has a variety of these much more compact, scalable, high-density reactors.
I would love to see a liquid metal reactor, a thorium reactor. I have no idea why we're not building them. I am positive that other nations will be building them. They are much safer, easier to use, more efficient, more compact. So most likely, and China is experimenting on this, so that they will certainly have thorium reactors.
You say about helium-3, and we know about moon. It's a lot of helium, but why no one countries except China don't try to colonize it and extract it?
I don't think China is going to try to take over the moon. What are they going to do? Land somewhere and put up a flag and say, yay, we have it. All you'd have to do is drop a rock from orbit and then they wouldn't have it. They're not going to do that. Now, will they, if they get to Shackleton Crater first, will they say, hey, we're mining this ice and the Outer Space Treaty gives us permission to mine here and our facility is this big and if you're going to be flying over it or near it, get our permission? I mean, the laws of the sea still apply in space. You can't come within 500 meters of another craft without their permission.
But no one try except them. They say, okay, we do it, but Russia not, the United States not.
As soon as China really says we're going to do it and something lands up there, I guarantee you, Russia, the United States, and the European Union will quickly say, we will do that too, even better, and we'll have another race. Now, it's, again, trying to seize the moon and hold on to it is not very practical. But if you have the moon, let's say they did, someone gain control of the moon, a mass launcher to put supplies into orbit is also a railgun if you fire it in the right direction. One tungsten rod dropped from space hits with 2 kilotons of force. You don't have to use nuclear weapons. The peaceful use of space is what everyone hopes and wants, and that's what the Outer Space Treaty is all about. And it's illegal to put weapons in space, right? No. It is illegal to put nuclear weapons in space. It is not illegal to put any weapon in space. Whoever gets there first had better be nice. You can put solar mirrors and shine it on a titanium sapphire crystal and fire a laser that would toast anyone coming toward you. Then you got to talk about trying to make your ship stealthy and all this stuff. I mean, it gets into the expanse. These things are going to happen. The moon will be colonized. It is an amazingly valuable piece of real estate because of the mass that you can launch off of it. And when you talk about the Hyperloop, you don't have to evacuate it on the moon. You just have an open rail and go. Well, you might want a tube in case somebody walks in front of it. But, you know, you could go as fast as you want. There is no air resistance. Mars, too. Hyperloop on Mars works incredibly well. You can go to crazy speeds before you start heating up enough for it to be a problem, because the Martian atmosphere is so thin. Yes, sir.
I was wondering about the rockets. Is there a way to make the 3-stage rocket out of all of the different thrusters you talked about?
Absolutely. You could have your first stage just be good old kerosene and liquid oxygen, your second stage nuclear thermal, and your third stage could be ion. Your nuclear thermal could stay in orbit so that it could be used as a tug to take things from lunar to Earth orbit and back and forth. It would have a 5 to 7 year operating period before you'd have to refuel your nuclear reactor, and it would be more efficient than anything else out there. If you can mine the moon, then you've got access to water. You've got hydrogen and oxygen. So none of these things are technically impossible. Every year we get together and talk about how we should go to Mars. We don't need some new, incredibly crazy technology. There are uranium miners right now that are allowed to withstand radiation dosages much higher than anything you would get on the way to or from Mars or on the surface of Mars. There are hot springs in Iran and some mountains in Brazil that are as radioactive as the surface of Mars, and people do fine. Now, the galactic cosmic radiation, that's a problem. You're probably going to have to use electromagnetic shielding or get enough water between you and those high-speed particles. Yes, sir. The scramjet is really neat. If you could use say an electromagnetic catapult with a scramjet, or if you use Skylon, Skylon's really cool. The problem is that you're only going to get about 5% of your mass into space. Our whole goal is to get as much mass as possible into space. The Skylon will be great for taking up small things and dropping them off. I personally think that you need to separate your cargo going to Mars from your humans going to Mars. Your cargo going to Mars can use conventional rockets or nuclear thermal rockets. You can use large masses. You could use an ion drive or whatever. Your humans going to Mars should be in a separate ship, I think, that is more shielded and a lot faster. And spinning so that you have artificial gravity. Because even with the myostatin inhibitors and your preservation of muscle mass, you're still going to have bone loss, eye changes, cardiovascular changes. You can spin your little centrifuge, and on the way there, slow it down so you go from Earth gravity to Mars gravity. When they get there, they'll already be adapted and ready to go. There's all kinds of assumptions that humans will fall apart, you know, if they live on Mars more than a year. But we've had people in orbit. They don't have any G's at all. They lift weights, they run, and they've been in orbit for over a year, and they're fine. You know, there will be some health consequences of the cosmic radiation, but again, we let people mine uranium, for gosh sakes. You're inhaling uranium particles. It's alpha emitting. Yes, sir.
Oh, sir, the way I understand it, Dr. Chang Diaz, the
Yes, sir,
Vacuum
in
rocket,
Houston. Yes, sir.
I understand that that his engine does not really work, and there was a lecture about it.
His engine works fine if you have 6 megajoules of energy to produce 400 newtons of thrust in low gear. Now, you're not using a lot of propellant, but again, it's xenon. If you want to colonize the solar system, you need to do it with hydrogen, oxygen, nuclear. You need to do it with things that you can resupply. But as far as putting a Vasimir in orbit, if you have nuclear power to power the thing, but how big of a nuclear reactor would you need? If this guy puts out 20 kilowatts, and that's the best the Soviets could do, how many would it take to get up to the 6 megajoules? That's a lot. It's a lot of mass that you're putting into orbit. You would almost be better just burning hydrogen and oxygen, producing your water shielding, and use the hydrogen and oxygen internal combustion engines to power your Vasimir. But Vasimir, you know, a lot of things work theoretically or under optimal conditions, so it would work if you had the power to do it. But there are other ion drives that seem to work better, that do not mass 10,000 kilograms. Now, again, there's pluses and minuses to everything. This thing has a low gear of 400 newtons, a mid gear at 80 newtons, and a high gear at 40 newtons, and that's just a 200 kilowatt, you know, that it's processing through. It's about 60% efficient. Some of the ion drives are more efficient than that. So there are a lot of things to be weighed, and my time is up. Thank you.
Your time may not be up if we don't have our next presenter. Is George Lourdes in the room? George?
If he is, he's running away.
All right, here you go, sir.
Thank you. I went to a presentation just yesterday, I think it was, where the speaker was proposing a magnet that is a coil, and
Yes, sir.
it makes use of the radiation either from the sun or the galactic radiation.
What it's actually doing is not using radiation, it's using the magnetic field lines to imagine this is how I pictured it as he was describing. Imagine a rare earth magnet sitting on my table right here. And I pull a vacuum, I put a chamber over it and pull a vacuum. I have that magnet in a vacuum. I put a titanium ring on that magnet. It just sits there, it doesn't stick to it, but it doesn't levitate. I put an electric charge through that ring. It will then levitate. What's lifting it? Well, of course, it's the magnetic lines of force coming out of that fixed magnet is levitating, is moving that ring. And that's what he proposes. There are very powerful magnetic fields coming from the sun. And I know very little about this, but he seems like a very smart gentleman, and he was saying 1 billion amps per cubic meter is how powerful these fields are. Now, the sun's an unimaginably powerful nuclear reactor, putting out an incredible electromagnetic field. So you put your ship with its coils, superconducting coils, in the path of this field line, and you put your polarity one way, you charge your superconducting magnets, and once you charge them, that thing's going to run down that line. It sounded like a pretty nifty idea.
Well, he says that you could get 1 G per second of acceleration, and it would take just a few days to get to Mars.
You could get even more out of it if you don't mind getting a really hard workout on the way there and being about an inch shorter when you get there. Compression fractures. But it is a very, very neat concept. And they've got to put something in orbit and test it and see if that works. If it does, it would solve a lot of problems. None of these ion drives. Now, you still need to get up into orbit because it's not going to work off Earth, or on Earth, I should say. But it will be very, very neat. It'll be a big game changer if it works.
Okay, Dr. Parker, an excellent talk.
Thank you, sir.
Let's visit 2001, A Space Odyssey for a moment.
Yes, sir.
We're going to build a ship to go to the area of Jupiter. Of course, it's not to find the monolith, it's to start exploring Europa and these other interesting moons that very well could have life on them. To make a long story short, how would you design that craft? What kind of propulsion? You know, in general, just a general overview.
Yes, sir. I would use a combined nuclear thermal ion drive. Nuclear thermal, so you get a burst of power, because the sooner you get to a good speed, the much less time it's going to take to get there. So you use your nuclear thermal, and you've got a nuclear generator. You're going to need it for your ion drive anyway. Might as well throw some hydrogen through it, heat it up, throw some hydrogen through it, and get some thrust out of it. So you use your nuclear thermal to get up to a good velocity. You run at a high efficiency ion drive after that, and your ion drive can use hydrogen gas. It's just not as efficient, but it's still, it doesn't give you as much thrust, but it's still good. Then you turn around at the midpoint, start decelerating, and your final deceleration would be again using your nuclear thermal. If you built your ship on the moon, it could be massive enough to have an insane amount of shielding. As long as we build and launch our ships from Earth, they are not going to be that big. Even with New Glenn, even with the big Falcon rocket, you're not going to get as much mass as you really need if you want to be launching a lot of materials and colonizing something or having a true spaceship where people can live and have centrifugal force and all that. You could spin, picture a circular city on the moon spinning at 1G. People could go there and stay, then they could go out and work on the moon. All you need to have on the outside of it is a little train that catches up to it and then slows down so you can get on and off. We could even call it Spin City. There are lots of ways to overcome the problems. If it turns out that 16G is not enough to keep people healthy, you could spin your entire colony on electromagnetic rails. Once you charge them up, it would keep moving. It's not going to take you a tremendous amount of energy. You'd have to supplement it from time to time because of losses, thermal losses and stuff. But you've got solar energy. You've got tremendous amounts of energy right there from the sun, at least for 6 months. Then you've got your nuclear during your other time. There's no problem to colonizing the moon or colonizing Mars that we don't currently have the technology to solve. It's amazing to me. Now, I am not a hippie. I was a U.S. Marine, and then I was an ICBM commander in the Air Force, commanding Minuteman II ICBMs. But if we can spend $2.3 trillion blowing up a country that did not attack us, we could at least spend $1 trillion getting a jump on the next century. Because who were the first to come to North America? The Vikings. Why didn't we know that immediately? Because they didn't stay. So just because we were the first to get to the moon will not give us any credit except a footnote in history if we don't go back and colonize it. The people who came here and colonized it were on the Mayflower and the others, and they're the ones that shaped this country, you know. Sadly for my ancestors, I'm half Comanche.
Has any television or movie production company approached you with the idea of you being technical advisor to some science fiction television series or movie?
No, but I do love science fiction, and I loved listening to the science fiction authors speak because they are the ones, the hard science fiction. They are the scientists that dream and tell us what's possible. Would we be running around with these little things in our pocket now if we hadn't watched Captain Kirk flip his open? We all like to, Star Trek's cool, but really the guy who developed cellular phones got the idea from, absolutely, and he got the idea from watching Star Trek. He said, why can't we do that? And he did. And the ion drive, the first ion drive to fly, what was it, Deep Space One? First off, Deep Space Nine is a Star Trek thing, and Deep Space One was the name of this ship because the guy who designed it was a kid watching Star Trek, and in one of the Star Trek episodes, Scotty was talking about an ion drive, and he thought, what's that? And he went to school and he started looking it up. Of course, back then, math, science, we were pushing toward a goal. So we were trying to educate people. If you are an educator today and you're trying to explain physics to kids, it is not simple. Our education system has made a spiraling nosedive. Most of the Nobel Prizes won in the United States now are not won by second, third, fourth, or fifth generation Americans. It's by first generation Americans or recent immigrants because they have educational systems better than ours.
Dr. Parker, thank you for your generous time and excellent.